This final section of series that we're going to look at, we're going to start taking a look at a couple applications of using series to do calculus operations. And so really two operations that we're looking at: use a power series to evaluate a limit and a power series to approximate a definite integral. Now, in the previous section, you might remember that we were able to find the Maclaurin series and then also the interval of convergence for a couple of these, okay? And also in the assignments, that's the same thing that you're being asked to do. So what we have here is we have a list of various Taylor series, and they're actually Maclaurin series centered about a equals 0, and there's summation representations, all right? So basically, let's just assume that we have verified that these are all, and there's a bunch more that we just haven't shown, but let's just assume that these are all going to be power series representations of various sorts of functions, okay? So we have e to the x. Whenever we have e to the x, we could write it in this form, okay? And then also, if we had something like cosine of x, we could write it in this form as well, all right? And we're going to use these to maybe evaluate a few of these sorts of series, all right? So let's take a look at a couple examples as to where we can use series to evaluate limits. And all we're going to do is we're going to replace whatever function we can that's not a polynomial with the power series. And then we're going to start writing out terms, and hopefully we'll be able to simplify. Okay, so, and we're going to use this above list. Okay, so now on an examination, what I would do is I would say something to the effect that recall e to the x equals this, or I would say recall that sine of x is equal to this. Okay, so I'm not asking folks to memorize these. Okay, and of course, but I would ask you to be able to derive these using the Maclaurin series, just like we did in the previous sections. Okay, so just be aware that on the examination, I might ask you to derive these by using the definition of a Taylor or Maclaurin series. All right, so but for these problems, I'm just going to say, I'm going to give you what the series looks like. Okay, so we're going back and we have the sine function, and we're just going to replace sine with this power series representation, and then we're going to write out some terms. So this is going to be the limit as x approaches 0 of, and I'm just going to put this in brackets, not that I have to, x to the 5th. And over here, let's just use this mess right here, okay? And we could put in some terms, and notice that we're just alternating positive, negative, and then we're going to use odd exponents, okay? So the sine function is going to be x minus, and we said it was going to be 1 over 3 factorial, so that's going to be x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. Now we still have these two terms, all right? So minus x plus a 6th of x cubed, all right? And by the way, this just goes on infinitesimal, okay? So I could just say minus dot, 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 okay? Because it just keeps going on forever. Right? Now, what we're going to do is we're first going to simplify by noticing that we have an x and a negative x, so they cancel out. 3 factorial we know is 6, and so we have a negative x cubed divided by 6 and a positive x cubed divided by 6. So those cancel out. So what we're really left with is the limit as x approaches 0 of, remember this is a positive here, so we would have x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And then that just keeps on going forever. And then divided by x to the 5th. Now, what I'm going to do is I'm going to factor out an x to the 5th from the numerator because all the terms have at least an x to the 5th. So this is going to be the limit as x approaches 0 of, if I factor out an x to the 5th from the numerator, that's going to be 1 over 5 fact minus x squared over 7 fact plus x to the 4th over 9 fact, and that just keeps going on forever, divided by x to the 5th. And notice that these are going to simplify and cancel. And so now we're left with the limit as x approaches 0 of 1 over 5 fact minus x squared over 7 fact. So just these terms plus x to the 4th over 9 fact plus, or minus, not plus, but minus, not that it matters, but just to be technically correct, minus da 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 da. All right. And notice what happens when we substitute 0 back in, that this just goes to 0 and this just goes to 0. Now this would be like an x to the 6th, which would go to 0, and x to the 8th for the next term, and then x to the 10th, and that would infinitesimally just cancel out all those terms, and this is what we're left with. Okay, so we're left with 1 over 5 factorial, which is 1 over 5 times 4 times 3 times 2 times 1, and then this is 20, and this is 6, so 20 times 6 is 1 over 120. All right. So that's how we can use a power series to be able to help us to evaluate limits. All right. Of course, we could use L'Hopital's rule, but we might need to use it 5 times. All right, at least maybe 6, to be able to get to some sort of answer at the end. And even then, it might not work because remember, we still have to have 0 over 0. All right. So just be cognizant that a lot of times L'Hopital's rule, it might seem to work, but it doesn't work all the time. All right, so in our next video, we'll take a look at one more of these, and then we'll move on to integration after that.